Welcome, folks. I think I don't want to take too much of your time, but I'd like to introduce Eric Feigelson. He's a professor in astrophysics at Penn State, and he'll be leading this course on time series methods for astronomy. And I believe there will be some guest lectures as well coming up. Mm-hmm. And he already has a syllabus, and I plan to attend some of those, but today I have to go away. So with that note, Eric.
Thank you, Sijit. It's a pleasure to be here. I missed the first semester of this Astrostatistics year-long program last semester, but I'm here this semester. I'm in room 174, and it's a pleasure to be affiliated with SAMC's effort right now. So let's talk about the course and go over the syllabus for a few minutes. Then I'm going to give roughly a 1-hour lecture, a lecture that I've given to over 1,000 graduate students of astronomy over in 14 countries and at Penn State over the years. The talk develops, but it's a motivational talk, sort of why bother doing any of this. Then we can have a break, go to the bathroom or there's coffee down the road. If you want coffee now, just walk all the way down this first hallway. Well, anyways, down the hallway, there's coffee and tea. And then I'm going to give an introduction to time series in astronomy, which won't take an hour. In fact, the time scale for this is 2.5 hours every Wednesday, 4:30 to 7. But I wouldn't be too surprised if sometimes we don't go all the way to 7. I hope you don't mind, but if your stomach is grumbling, maybe you'll be happy. Who knows, okay? But all of us will have somewhat late dinners on Wednesdays if we take the class. Okay, so let me go through this. I've never taught the 3 universities at the same time. It's just an amazing system you have here. So UNC and Duke and NCSU, I assume you know what these numbers mean, and I don't. If you have any questions about the course as a course, please speak to Sue McDonald, whose office is right around the corner here, or email her about the course aspect. My job at the end, in terms of the course, is to send a grade, which apparently is pass or fail. And all I could say is I certainly don't expect any failures. Although I'm told at UNC there's something called super pass or high pass. Oh, yeah. So there we go. Maybe you can earn a high pass. That's amazing. Okay, I never heard of a high pass before. There will be these videos. In my opinion, the videos may be valuable 2 years, 4 years, 6 years down the line, because astronomy in time series issues in astronomy are growing, and something's going to happen in astronomy around 2021 with a new telescope called the Large Synoptic Survey Telescope. It is the national project of America. $1 billion for one instrument serving thousands of astronomers with time series. 40 billion time series. Whoa. Most of them not very interesting, perhaps. But only some tens or hundreds of millions of them will be interesting. So I think time series is going to grow. And this is not just me. This is one of the motivations why 2 out of the working groups here, 2 of the most active working groups here, this year are on time series problems in astronomy. So this class merges closely with the SAMC research effort going on right now. And that is why we're doing it. I want you to know that I'm quite confident that there's never been given a course called Time Series Methods for Astronomy ever in history. Maybe I should put methods. I forgot an S there. Okay. This is such a new topic that no one's ever thought about a course. Okay? So you are the guinea pigs, but you also are on the frontier of a research area which is new, but growing And $1 billion is not nothing. And that's not the only thing. There's other time series instruments out there. I've been working with a NASA satellite that only cost $700 million, and it produced only 200,000 time series. But this is an example of what's going on. It's a big growing scientific enterprise. Okay, the course website is, there's no reason why it won't work in this room. www.2.astro, PSU is Penn State University, /users/EDF, Eric D. Feigelson, that's EDF. And the most recent one is TSMA, Time Series Methods Astronomy, TMSA, SAMC 2017. There we go. It is already populated with this syllabus and with the 2 lectures I'm going to give today. Okay, so hopefully it will be populated. It will then have homework assignments. It will have data sets, R scripts. Okay. Can I ask, how many of you know R as a programming language in statistics? Sir, are you the astronomer?
Maybe.
Are you an astronomer?
Yeah.
Okay, okay. So why don't we say R is going to be mostly for you to learn, and there's no reason why you and I can't spend another hour and stuff. So I might give the introductory part really fast.
Okay.
It's going to be next week. I'll do introduction to R. For the rest of you, we'll go through the introduction really fast. But even if you know R, you still might like parts of my introduction. In other words, some of it might be, oh, really? I didn't quite know that. That kind of stuff. So we'll do a lot next week. And you, I'm sorry, what's your name?
Charlie.
You're Charlie. Good.
Yeah.
So Charlie, you'll try to keep up. And then if you want to go slower and stuff, do this. But my experience, I've taught R in 2 hours to 1,000 astronomy grad students. They're smart and they're quick at this kind of thing. So do you happen to know IDL or MATLAB? No.
Not really.
Okay. It's a very similar language to IDL. Do you, of course, know Python?
Yeah.
It's not that similar to Python or C. Okay. It's more like MATLAB or IDL. It's a high-level scripting language.
There are lots of online resources as well.
Yes, that's right. You can even take the course. Good point. Thank you. Okay. The date in Venu is Wednesdays, all semester long, and March 15th is spring break. And it starts at 4:30. We started 5 minutes late. And we'll go to 7, or no later than 7. This is the room. You're here. The fact that you're here means you know the Venu. My name is Eric D. Feigelson. I am a professor of astronomy and astrophysics. I'm an X-ray astronomer by training. But I stumbled into the stat department as an assistant professor in the 1980s. And I asked a question. And I asked a question, and I drew something on her blackboard, on the consultant's blackboard. I said, I have an X, I have a Y, I have a bunch of points. They obviously fall in a line. But my satellite that measured the Y variable didn't actually detect some of them, and I have these downward-facing arrows. How do I draw the line with what we call upper limits in brightness or some other property? And her eyes widened. She reached up to her shelf, pulled out a textbook. It was the 80s, so it was the very first one. And it had that diagram upside down on the cover. And she said the course started 3 weeks ago, and I took a graduate course in the stat department on survival analysis, which is a field of statistics, of applied statistics, developed mostly in the 1970s and 80s. And now there's several textbooks. It's very practical. It's used by quality control engineers. It's used in pharmaceutical testing and research. And it's just useful. And believe it or not, if you multiply by -1 to get left censoring instead of right censoring, it's useful in thousands of astronomy research articles. So I want you to know that that was the best paper. Oh, the instructor and I wrote 2 papers in the Astrophysical Journal that did nothing but summarize the textbook, multiply by -1 at the beginning and -1 on the other at the end. Oh, and we changed the nouns from survival time to galaxy luminosity. Multiply by -1, change a noun. the best papers I ever wrote in my career. 1,000 citations. I couldn't believe it. I just couldn't believe it. I didn't do anything. We didn't do anything. So I went to the department head and I said, stat. I said, is there anything else you have for astronomers? And he must have thought probably I was crazy. I mean, it's like going to a physics department head. Do you know any physics? What do you think we do in stat? But no astronomer had ever walked into a stat department successfully until me. I'm not joking. So he teamed me up with a guy recently arrived named Jogesh Babu, and Babu and I started talking, and we haven't stopped talking in something like 28 years. So we're friends, and if you were here last semester, you met Jogesh. He's back at Penn State teaching. And so that's how I got started. And I'm now convinced that astronomy is just, astrostatistics is wonderful. You guys in stat have a vast amount of things, and that's what this first lecture is about for us. Hello? Please sign in and take a syllabus. And I haven't said anything yet of any interest. My name is Eric Feigelson. Okay. If you're listed there, just sign your name. But if you're not listed, fill it out so we know who you are, and Sue McDonald will take care of it. So that's how I did it. So Jogesh and I, we ran research conferences called Statistical Challenges in Modern Astronomy for 20 years. We run summer schools. We then wrote a textbook that comes from the summer school, Modern Statistical Methods for Astronomy with R applications. R is their language. It is the language of statisticians by statisticians for everyone. R is used by 2 or 3 million people except astronomers. Okay, astronomers are really stupid not learning R. Okay, because it's vast and friendly and capable in many ways. The main challenge is to know enough statistics to use it. Okay, and that's the challenge for astronomers, and that's why we spend most of our time talking to astronomers, not to statisticians. But I only have limited experience talking to statisticians. But I'm not going to teach that much astronomy and astrophysics. I mean, it would be like, it's just not what I'm just going to do. Okay? I'm more going to teach the interface between astronomy and James Long did it last semester. But I'm teaching only time series methods because that's a growing field. So, hi, what's your name?
Dear.
Dear. Pleasure.
William.
Whaley. And are you statisticians or astronomers?
Oh, statistician.
Statistics, astronomer, statistics. You're all alone. I'm sorry, Charlie. Okay. But that's okay with me, okay? I'm more used to speaking to your crowd than to these guys. For you, you're going to have trouble with the nouns. If I use the word quasar, you're not going to know what that means. If I use the word pulsar, you're not going to know what that means. You're not going to realize that pulsars and quasars have nothing to do with each other. They're totally different. And they each got their Nobel Prizes, but a long time ago. And okay, right? You're not going to know that. I'm not going to teach it. I'm not going to teach much astrophysics. But you certainly will get a feeling of why and what we're doing, particularly in my second hour today. Okay, the course description. You can read it as well as I can. Is going to be, I'm going to do sort of introduction, including in base fundamentals of time series analysis. That's in any textbook. That's only going to last maybe three classes, maybe 4. By the time I get to the last one's frequency domain, it happens to be at the end, but it's really introductory. And then we need this foundation. We need a shared foundation of methodology. I'm sorry if you already know some of it. But then we're going to get to the bulk of the central part of the class. The second part is a combination of graduate level methodology, but in the context of research. And here, the SAMSI scholars who are coming in this semester are being featured. Ashish Mahabal, Becky Dawson, Eric Ford, and 2, if not 3, of our postdocs who are here, David Stenning, David Jones, and talk if you want to do it. There's certainly at least one empty spot if you're interested. The actual schedule is likely to change. That's why I have version today. But I don't think it will change hugely. It will look something like this at the end. At the end, I hope you present projects. So that gets down to assignments and grading. So first I'm going to offer, this is now for students taking it for credit. But if you're not taking it for credit, you want to do it, it's fine with me. I'm going to give you 4 homeworks starting next week. And they'll all be based in R. And most of them will involve data sets that I will provide. In fact, that's the way it's going to happen. I will provide data sets, and you will do it. We're going to do some tutorials even in class, particularly next week. Please bring a laptop next Wednesday with R installed. www.r-project.org. That's where you install it. It takes 1 minute to install on Windows, Mac OS, or Linux. It's all available in a minute, just like an app. It's an app that does all of modern statistics. It's a heck of an app. Okay, it's really huge. It's amazing. Okay, so we'll work together. Next Wednesday will be tutorial, not lecture. Except I'll tell you about where R comes from at the beginning for a few minutes. So there'll be 4 homeworks. The homeworks will be 60% of the course grade. And then as we get rolling, maybe not at the moment now, but maybe 3-4 weeks from now, we'll say, okay, it's time for each of you to think of a project. Hopefully you already are doing something that's related, okay? And now that I realize it, I normally would say, oh, your project has to be astronomy data. But now I'm beginning to wonder that some of you may be statisticians doing time series in some other field. So I'm not going to be narrow-minded. So if you want to do time series in earth sciences, or time series in biological sciences, or time series in engineering, or even in business, the main thing is that each one of you, you're a small group. We'll talk about it one by one, and you'll tell me about your data set and what problems you have. The most important thing is to have good questions that are not too impossible to answer and not too easy to answer, so that you not only for your project use basic methods in R, but some advanced methods in CRAN packages. And if you don't know what that means, really, don't worry. You'll be seeing CRAN packages as we go along in the first few lectures. This is where the really substantive work is being done by R for challenging research projects. And then I'd like you to write me a paper at the end. Okay, it doesn't have to be polished and perfect with beginning and middle and end and all just gorgeous. But it has to have a functioning R code, and you'll have experience doing that from the homeworks, where you'll be giving me R scripts, emailing me R scripts, and I will run them. If they don't work, that's not good. They have to work, okay? Even for the homeworks, I don't want just an R script. I'm not going to give homework assignments that have a single answer. The answer is 42. It's just not going to be like that. It will be like, take this data set and explore these kinds of things, maybe using some of these functions here or something like that. And so each one of you are going to do something individual, exploring using in a certain direction. I will assign the direction in the data set. In the case of your project, you will assign the direction in the data set, but we'll talk about it. So maybe by roughly week 9, week 8, maybe week 8, each one of you who are taking it for credit will have a project in a data set. And the second half, no homeworks. You'll be working on your project. Okay? So it is a 3-credit graduate course. It's not nothing, but it's not the most murderously difficult course you've ever taken. It's intermediate. There's work, but not too much work. Okay? That's my view of it. What do you think? I just invented this. You know, you like 60-40? You want 50-50? I don't know. Maybe it'll only be 3 homeworks by the end. I don't really know. Okay? But something pretty close to this. Okay, let me know. You can send me an email if you have any questions or suggestions to improve. Like, oh, I'd really like to do such and such. Maybe I'd never thought of it. Sure. By the way, to contact me, lead instructor, EDF at ASTRO, PSU, PSU is Penn State University. Okay, EDF is my initials. Okay, oh, yeah, and this is the tentative schedule. Any questions, problems, or suggestions about the syllabus? You feel comfortable? Whether you audit or take for credit, or you just sit in once in a while, you just say, hey, I really like weeks 5, 6, and 7, but I don't like the rest. I don't care. It's up to you. Obviously, if you take it for credit, you're expected to be here every week. Okay? That's it. Okay, let's go to the first motivational lecture. Why astrostatistics, or what is astrostatistics? Okay. So I figured if you want to know what astrostatistics is, let's ask what is astro and what's statistics. And since most of you are statisticians, I'm actually going to spend a few minutes on this first slide. I normally don't, okay? So astronomy is actually a code for 2 words. Since the 20th century, it's called astronomy and astrophysics. My department changed its name from Department of Astronomy to Department of Astronomy and Astrophysics around 1980. Okay. And representing this code. So the astronomy part is looking out at the sky, the nighttime sky, unless you're studying the sun. So we could use a telescope that we were born with. Aperture is about 2 millimeters. Focal length's about 5 millimeters. It's not a very, the detector refreshes 20 times a second. It's not a very good detector for nighttime use, for faint things, little specks in the dark. Okay, also mine are out of focus. Ah, good, I feel better. Okay, so I've got a pretty crappy telescope. Okay, so instead, starting with Galileo in the 1609, roughly, he had an aperture this big. Newton invented one this big. Today, a modern telescope is, 8 meters diameter, so it's about the size of this room. It's usually paraboloid, so it makes an image when light reflects. So the eyeball has gone from a couple millimeters to 8 meters. Square that for area, for sensitivity. So it's gone up 8 orders of magnitude, 10 to the 8 times more sensitive, at least. We also integrate for more than a 20th of a second. Particularly, we now have CCD detectors, which are nearly 100% quantum efficient. Almost every photon that lands makes an electron signal. And we might read it out every few seconds. Even Hubble Space Telescope, they keep it on. They just read it out after half an hour. Extremely sensitive. Another couple orders of magnitude of sensitivity. The net result is we can now see things 30, 25, 5, 10 to the 10 times fainter than what you can see with your eye, approximately. In addition, you have to know a little bit of physics. The electromagnetic spectrum does long waves of radio, about like that, infrared, and a teeny weeny range we call visible light. That goes from red, green, blue. And then it goes ultraviolet, X-rays, gamma rays, very short wavelengths. So the human eye sees about a factor of 2 in what's infinite. We now have instruments that go from 10 meters to, gosh, it's even hard to know. Direct imaging, the direct telescopes. It's 10 to the, I can't even think of it. 10 to the minus 10 meters, 10 to the minus 15 meters, 10 to the 2 meters, 10 to the 17. 17 orders of magnitude in wavelength, approximately. I probably got it wrong. Okay. So they're called radio telescopes, infrared, visible light, ultraviolet telescopes, X-ray telescopes, gamma ray telescopes. Technology changes every time. Every band. We're really good technologists. We're really brilliant. The most amazing, sensitive receivers and detectors in the universe. I'm not joking. Are at a certain wavelength, around a centimeter, we actually have quantum perfect detectors. The most advanced alien society does not have a better one in the universe. So we're really good at astronomy. Okay, that's this. We study the things in the solar system, the planets, the asteroids, dust. We study stars in the Milky Way, where the sun is, of course, the nearest star, but there's hundreds of billions of other stars in the Milky Way. The Milky Way is this band you see on a very clear night away from a town. Other galaxies were discovered around 1920, when we found out that the universe is full of them. In fact, the universe is infinite in size and in age. It's not infinite in age in the past. It began 13.7 billion years ago. It's infinite in age in the future, and it's infinite in volume, and has an infinite number of galaxies, of which we see approximately, we can see hundreds of billions of them. I think that's a good number, but I'm not sure. Maybe it's too small. And there's a lot of gas that hasn't collected in stars or planets yet, diffuse matter. And there's a lot of stuff that isn't even matter. There's dark matter, we don't know what it is, and dark energy, we don't know what that is, but we know it's there. That's the study of the universe itself. Astrophysics, that's astronomy with telescopes, is the understanding of all of the above using the knowledge of the physical processes and the nature and constituency of matter, properties of matter, that we learn on Earth in a lab. So when you go to a chem lab or a physics lab, you learn something about atoms and spectral. Let's say you burn some copper in, it turns green, has a spectrum. There's something about quantum mechanics. Let's say you take gas and you put pressure and density and you look at Boyle's law or something in an elementary class. That's thermodynamics. Well, that's the kind of thing. Gravity, thermodynamics, quantum mechanics, electromagnetism, all the things we learn on Earth that lead to our understanding of physics, useful for, let's say, cars and computers. We have great understanding of physics on Earth. Amazingly, it's the same physics in the galaxies. That didn't have to be true, but it is. It's universal. There's no violation of physics ever found anywhere in the universe yet. The same physics is going on everywhere. One universe. Universe. One. Okay? So because the physicist tells us all the laws, the astrophysicist has an easy job. We don't have to figure out the physical processes. We just have to apply them. We're like applied physicists. But we're applying them we can't bring the star or the planet into the lab and cut it open and work on it. So we apply it to our observations, mostly of light. So a lot of it is how bright is it, and does the brightness change? What's the spectrum like? Does it show atoms and molecules? And we learn pressures and densities and compositions and things like that. And then we infer, oh, that's what a star is made of. That's what a galaxy is made of. Oh, that's the processes going on. So I have, for the statistician, and Charlie, I hope you'll forgive me, I completely ruined all of astronomy and astrophysics by summarizing on 2 slides, all of astronomy on 2 slides. Overview. So the universe started with a big bang 13 billion years ago from a state we don't understand that unifies general relativity by Einstein of gravity and quantum mechanics. And that unification's they've been working on it for about a century, and it still hasn't been totally successful. So we don't understand that very well. Then the universe grew from microscopic to about the size of a basketball in 10 to the minus 35ths of a second. And it's called inflation. And then in the first few minutes, we made hydrogen and helium, and a little bit of matter appeared in the universe. It's actually not much matter. We're actually a very minor part of the universe. The cosmic microwave background is the light from this that comes out of inflation and comes out of a certain phase after inflation. And that's studied as a spatial field, not as a temporal field. So we will not talk about that in this class. Then gravity, the universe is expanding, but the stuff in the universe, mostly the dark matter, but also the regular baryons, which means regular electrons and protons and neutrons, start collecting and making little blobs and making the first stars, the first galaxies, and the first black holes. Those are the quasars, by the way. And then we then go forward in time over billions of years, and we make more galaxies, and each of them make more stars and make more planets, and that sort of continues on and on and on. So in a certain average galaxy, called the Milky Way galaxy, a certain average star got formed, called the Sun, with 8 planets orbiting it in more or less circular orbits, called the planets, of which the 3rd planet happened to be at a favorable location for liquid water. That's Earth. And that one happened, there's a lot of molecules around, and many of them are carbon-based molecules, known as organic molecules. And somehow or another, the biologists have really messed up. They haven't figured this out. But somehow or another, the simple carbon-based monomers that the astronomer sees combined into polymers like RNA that reproduced and made more RNA and DNA and made vesicles and made cells. And the cells became bacteria. And for 3 billion years on the 3rd planet around this average star, there were bacteria, including photosynthetic bacteria that changed the atmosphere, making it oxygen-rich. It's very rare in the universe to have oxygen, free oxygen. It's very unstable to combustion and chemistry. And then, for some reason nobody knows, 500 million years ago, the bacteria started becoming more sophisticated. Sponges and worms and trees, dinosaurs, and people, and puppy dogs. Okay, we're very recent. We don't know why things became, we don't know how the first bacteria came, and we don't know why it started making sophisticated more organisms, but it did. We understand some of the process, particularly DNA evolution. That's understood very well. So that's called the biosphere. And we live on one of these planets. That's called earth science. So that's biology. That's geology. There's a lot of chemistry as well. Those are the fields of science in every university. Astronomy is studying this whole sort of environment around it. We also know the future. The galaxies are moving apart forever. The stars are burning hydrogen to helium, become red giants, then burn out. They'll all get dark. Don't worry. Hundreds of billions of years from now, don't worry about it. It's not too depressing if you think how long it is. Okay. Now, I'm going to give you a little more about sort of this thing. That's my second slide. We learned in the 20th century, from roughly 1890s to about 1970, we basically understood the physics, astrophysics of stars, the sun. The sun we understand all the way in the interior to better than 1% in all relevant numbers. Other stars, not so well. Okay, so it starts off with the gas and dust that's in the Milky Way, and gravity pulls it together in the cold places, and stars and planets form by gravitational, and then it has angular momentum, and you get the spinning disk. That's where the planets form. If it's the right planet around the right star, then it's habitable. And you can get life at least once. We may be the only case. Nobody knows. The biologists can't answer that one yet. Most stars spend most of their time as main sequence, burning hydrogen to helium in the core. The sun's not really doing much on the outside. It's all happening in the very middle. It's hidden away. It's like hydrogen bombs going off in the cores of stars. billions of them every second. You're glad it's hidden away inside the star. They're dangerous on the surface. Hydrogen to helium, hydrogen bombs. When you run out of hydrogen, the helium burns to carbon, nitrogen, oxygen, and all the way up to iron. That's very nice because we need the carbon and the oxygen for us. We need to walk on silicon and oxygen, rock, okay? So that it all comes from red giant stars, which then blow out these interesting elements out into the Milky Way, both slowly and through supernova explosions. The supernovas make the rare heavy elements like gold. Gold is expensive because it comes from supernovae. It's rare. Only a few massive stars go supernova. After they're finished, they leave behind some compact things, collapsed stars, white dwarfs, neutron stars, black holes. Each one of that is a Nobel Prize. A very amazing physics. By the way, these things are often highly variable in their emission. You throw some gas onto a white dwarf or a neutron star or a black hole, it goes in X-rays. And the stuff that doesn't go into the compact stars goes back and into the interstellar dust. So the next generation of stars has some carbon, has some silicon, has some gold. You can make a nice planet. So the first generation of stars, there's no planets, except maybe Jupiter. Third generation, us, nice place, Earth, great place. So what we know in our daily lives is part of the universe. It's integrated. We're not remarkable. We are remarkable in our sophistication. But chemically, in just the existence of this kind of structure, there's a lot of planets. We'll hear about that later. There are a lot of planets, a lot of Earth-like planets. How do we know? Time series analysis. It's all time series analysis to do exoplanets, to find them. That's one of the main motivations for modern time series analysis in astronomy.
Why does it stop at iron?
Physics, nuclear physics. Go take a graduate course in nuclear physics. I don't really, it's a mess. It's the most stable nucleon is iron. So it's a complicated mess. Quantum mechanics, it's very complicated. Okay, so that's astronomy. You've heard it for the first time, okay? You and I, that's what we do. Okay. So then you go to statisticians, say, okay, well, what's statistics? You expect a nice clarity. Ends up there's no clarity at all. There's no consensus at all. Every time you look at Wikipedia, they change the wording of it. It's just crazy. So R.A. Fisher is the most important statistician of the 20th century. He's sort of like Hubble and Eddington and 10 other famous astronomers wrapped together. We don't even have anyone in astronomy as important. So he wrote in 1922, I think he was roughly a graduate student in 1922. He was very young. He was a genius. He started as an undergraduate, revolutionizing his field. Briefly, in its most concrete form, the object of statistical methods is to reduce your data. Well, I don't know, Charlie and I, we're used to this. We keep on getting all this information from the detectors and the receivers that we have, and gigabytes and terabytes and even petabytes. And we reduce it down so we can publish a paper with kilobytes of information so we can understand it. So I think we understand that. Reduce the data. Okay. Wikipedia said statistics is the mathematical body of sciences that pertains to the collection, analysis, interpretation of explanation. Now that's not reducing, that's interpreting the data. Use the word modeling the data if you have a mathematical model, maybe from physics. And also to present visualization of the data. The next year they took out the word mathematical body. That's interesting. No more math and statistics. That's crazy, I don't know why. Now this man is still alive. I just saw him in London. He's about 90 years old. Sir David R. Cox. The Queen loves her statisticians. Okay? Oh, Sir R.A. Fisher. Sir David R. Cox. So he's still alive. He just won the big prize that they gave, International Prize. He writes many books. Wrote many books. This is one of his early books. A statistical inference carries us from observations to conclusions about the populations sampled. Now, this is not all problems in astronomy, but this one's particularly useful for astronomers, in my opinion. Because what it means is that the galaxy has, let's say, 1 trillion stars. Even LSST isn't going to see more than 1% of them. Most people, astronomers, work with, an incredibly tiny fraction of the underlying population in just one galaxy. There's an infinite number of galaxies. So that means that we're dealing with samples, tiny fractional samples of very, very large underlying populations. Now, the astronomer usually doesn't think about it this way, but I claim. Let's say you're doing a paper or dissertation on, maybe you have a collection of 500 Seyfert galaxies. You don't even know what a Seyfert galaxy is. Don't worry about it. Okay? Has a bigger black hole in the middle. Don't worry about it. You're not really interested in your 500 Seyfert galaxies, I claim. You're interested in Seyfert galaxies. The processes by which black holes form and gas falls onto them and the interaction and feedback it has on the host galaxy and that, blah, 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 all the things that we're interested in. We use the 500 to understand it. That's what he's talking about. To go from samples to populations. So that's a theme which I think astronomers sort of intuitively know. We just rarely sort of say it very clearly. Okay, George Box just died. He was in his 90s. He was R.A. Fisher's son-in-law. And he had a very strange thing to say. It's strange to astronomers. And really all these 20th century famous statisticians are incredibly pessimistic. They're not pessimistic about reducing data. They're pessimistic about the relating statistical methods to science. So George Box famously said, essentially all models are wrong, but some are useful. George Box must not have known an astronomer. Ladies and gentlemen, when a planet goes around a star in an elliptical orbit, it's not wrong. We know those equations. They're right. They were first written down in the 16th century by Kepler. Understood mathematically by Isaac Newton in the Principia Mathematica Physica, the mathematical principles of physical phenomena. We've known celestial mechanics, been doing it since the 1700s. It's not wrong, Mr. Box. Why does Mr. Box say this? I don't know. He spent his time talking to psychologists and sociologists, probably. They don't know anything. Social science, they don't have laws. So their models are what I call heuristic. They just make them up. We have heuristic laws too, by the way, in astronomy. But we also have physical ones too, physical models. C.R. Rao, also in his 90s, the most decorated, Fisher's last living student. Wrote 20 books also, one of the great figures. Jogesh Babu was his professor. Okay, Babu and Rao have written papers. He quoted Osiander's preface to Copernicus. And Osiander was Copernicus's uncle. Copernicus said this: the sun is in the middle of the universe, not the earth in the middle of the universe. But the Catholic Church didn't like this in the 16th century. And so Copernicus wouldn't publish until he died. He published on his deathbed, and his uncle wrote a preface. Don't worry, he says, there's no need for these hypotheses to be true, or even anything like the truth. They should just yield calculations which agree with observations. But the models are not right. They're just useful. And D.R. Cox, as an old man, his last book, The Principles of Statistical Inference, writes, the object of statistical inference is to provide ideas for the critical analysis and, as far as feasible, interpretation. He's not even sure you can interpret data. The extremely challenging issues of scientific inference, science, biology, chemistry, physics, astronomy, may be regarded as synthesizing lots of different conclusions into a coherent whole or theory. And the use, if any, of quantitative notions of probability is unclear. These guys are depressed. It's really weird to me as a physical scientist. I don't agree with him. So here's a quote from a less famous person, not knighted by the Queen of England. His name is Phil Gregory. He's a retired Canadian radio astronomer who wrote a lovely book on Bayesian inference for physicists and astronomers. And this is from his preface. The first sentence, the first part, is straightforward, what's called scientific methods, positivism, like Karl Popper, 1950s. The goal of science is to unlock nature's secrets. Our understanding comes with the development of theoretical models, which are capable of explaining the existing observations, so you can explain. But you might have maybe 3 different models that explain it. But you make predictions, and maybe only one of them predicts the next observations. And you falsify the other ones. And you make progress in your understanding. You actually understand and unlock nature's secrets. Scientific method. Now this is the new part. Fortunately, a variety of sophisticated mathematical and computational approaches have been developed to help us through this interface. The interface between astronomy, the data, and astrophysics, the physical model. To go from astronomy to astrophysics is called statistical inference. The math needed to go from astronomy to astrophysics is statistics. Thank you, Phil. This guy here. By the way, Phil Gregory, did he show up at SAMC? I don't think so. I don't think he showed up this time. Okay. He's a good guy. Knows a lot of statistics, very sensible, good papers. So Joe Gesh and I, Babu and I, we're really positivists. Okay. So this is now my synthesis of what I just sort of been showing the last few slides from 20-odd years of talking to statisticians, but still being an astronomer and astrophysicist. I think the application of statistics can reliably quantify. It's no longer you look at the data and you look at it and you say, it looks pretty good. Okay. Astronomers have even words for that, something called chi by eye. Ever hear that? Okay, no. Methods that quantify information that's embedded in your data from your CCDs or your detectors or your satellite telemetry. And the statistics can not only help you understand the data, but can help adjudicate the relevance of theoretical models. Now that's my way of saying, okay, D.R. Cox and C.R. Rao, I'm listening. Maybe we can't absolutely firmly confirm, for instance, we cannot prove a model is right. The only proof is in math. 2 + 2 is 4 is a proof. But this complicated evidence leads to the scientific inference that there are lots of planets out there. It's not a proof. But it is a preponderance of evidence. And it grows and grows and improves and improves. It's very consistent. So we can adjudicate different theoretical models. But this use of statistics is not simple. It's not straightforward. It's not mechanical. The typical older astronomer of my generation views statistics like I view a screwdriver. I'm very bad at fixing things in my house or anything. I'm just lousy at it. In my basement, I have 3 screwdrivers, a hammer, 2 wrenches. If something breaks in my house, I say, okay, I'll try to fix it. And sometimes I do it, but it's lousy. Sometimes I can't even do it. So when something breaks in my house, I've learned to not fix it. I'm lousy at it. I call up an expert. And it's usually he comes with a truck. And he opens up the truck, and there's 1,000 tools in his truck. Things I don't even know the names of. And he looks at my problem. He goes to Home Depot and gets some things, takes out 3 tools that are the right tools, does a brilliant job fixing my house. That's what the statistician does, can do for the astronomer. They know how to think about that kind of problem. They know how to choose 3 tools and go to Home Depot and buy the right stuff. I don't know any of it. I'm really bad at it. So that, Charlie, is what you're going to get by sitting here for a semester that your professors typically haven't done. Okay? They're stuck the way I was stuck. Most of my generation is stuck. In particular, I think the astronomers should spend a lot of time exploring their data without thinking about the models, just exploring the data. Is it full of junk and mistakes? Is it beautiful and clean? Is it what kind of is it multivariate? Is it etc.? Just explore it without too much prejudice. You might even learn something brand new you didn't expect, like outliers that might be interesting. Then you have a problem. You obviously collected your data because you had a question about your stars or your galaxies, your planets or your cosmology. And so, but you got to state it in a mathematical way. So write down a formula. You don't have to. I mean, you can write down sort of simple formula like, oh, linear regression, y equals a plus bx. There it is. There's math. Nothing wrong with that. A lot of social scientists do that. A lot of astronomers do that. We tend to do log of the variables, so we call it a power law. It's basically linear regression. So they're heuristic models, or they're astrophysical models based on quantum mechanics and gravity and thermodynamics and all radiative transfer and all the complicated models that we have in astrophysics. Okay? So I don't care what it is. Could be complicated or could be simple math. Then you choose statistical methods, and by that I mean things like least squares method, maximum likelihood method, and Bayesian inference. And more or less, I've taken you through 200 years in that sentence. Least squares was 1800 to 1820. Likelihood, R.A. Fisher, as a graduate student, invented likelihood and maximum likelihood. Often they're the same result for a whole class of models called linear models. They're the same. Bayesian inference can be viewed many ways. It could be viewed as totally different, or I like to view it as maximum likelihood when you weight the likelihood by some prior knowledge. And if you don't have prior knowledge, don't call it Bayesian. But if you do have prior knowledge, either from the astrophysical constraints, let me give you something. There's no such thing as a planet with negative mass. Negative mass doesn't exist. Here's a prior constraint. There's no such thing as a star with negative brightness. So zero avoidance is very common in physical processes. There's a prior. But sometimes we have more complicated priors. We actually know things either from the astrophysical theory, or we know things from the prior observations. You may be doing a dissertation on 500 Seyfert galaxies, but people have been studying them for 70 years. So this prior information that's really quite reliable, you can use it to weight your likelihoods and improve your scientific inferences with Bayesian inference. That's the purpose of Bayesian inference, in my opinion. That's the method. There are other ones. There's computational methods, algorithms as well. Now you got to calculate it. Do you know what most PhD astronomers actually do with their time? Do you know what most astronomers who are working on a PhD do with their time, most of the time? We're not at telescopes. We're writing software over and over for years. Most astronomers are programmers, often excellent programmers. I have news for the astronomers. You never have to write a statistics program again in the rest of your life. It's all in R. Now you have to explore your data, you have to manipulate your data, clean your data up and stuff. But the actual coding of a statistical calculation has already been done by people who know how to do it. They're called statisticians. Some of them are even specialists. They're professors of statistical computing. Those are the people who wrote R. They're around the world. They're in New Zealand. They're in Germany, in the United States. And they've spent thousands of man-years, people-years, writing R. So it now has almost all of modern statistics in it. So you don't have to write codes anymore. All you have to do is script around the code. Okay? So I've had 2 PhD students at Penn State do their dissertations with me in R. In each case, the whole dissertation, don't get jealous, Charlie, was a couple hundred lines long. Powerful things can be done in 5 lines. You will learn this from me because we'll be doing this several times in the early part. And your homeworks will be like that. You will learn how to do this. R is really cool. R is great. I'm not against Python. It's a general purpose language, and it has a fair amount of statistics, particularly in machine learning, but nothing compared to R. It's not as integrated together. It's not designed for it. It has a different purpose. And then you got to be evaluation. Sometimes, for instance, let's say you have 1 million Seyfert galaxies. Well, almost no model will ever fit 1 million objects correctly. You'll always be statistically significantly away from it. It might only be 1%. So statistically, you falsified the model, but scientifically, hey, look, it's good within 1%. That's great. See what I mean? The statistical result is not always what you want scientifically. Eventually, you have to go walk away from the statistics and be a scientist. And that's what D.R. Cox was saying. Scientific inference is not just statistical. Statistics is a tool, a suite of tools, a truckload of elegant and powerful tools. But it doesn't actually do the work for you. I mean, you have to think. So spend your time, astronomers, thinking beforehand and thinking afterwards, and don't spend your time writing codes. Not interesting? No one but me says this. Okay? I showed this slide at Space Telescope Science Institute in Baltimore. They run the Hubble Space Telescope. They're now going to run the James Webb Space Telescope. Think of that as $20 billion of your taxpayer money, okay, over 30 years, 40 years. And one of the senior guys, who's a friend of mine, comes up to me and says, Eric, he says, you scared me. You made me think I spent 25 years, I haven't done it right. And I said, Massimo, look, you're smart. Astronomers are smart. They're very smart. They know quantum mechanics. They're smart. They're very quantitative, but they just don't know all the methodology. So what the astronomers tend to do, my generation, Massimo's generation, is we tend to use a very few tools very carefully. And we tend not to make mistakes, bad mistakes. So the literature is not full of like terrible errors. What it's full of is sloppiness and inappropriate methodology, the lack of precision, the lack of reliability, not enough testing of how reliable the results are, not doing something 3 ways and they all confirm each other. You just feel so much better. What if you did it 3 ways and you get 3 totally different answers, and the one you thought you were doing maybe isn't reliable? That's where astronomers go wrong, by not knowing enough statistics. And those of you who are statisticians, which of course most of you, maybe someday you'll be working with some biologists or some engineers and stuff. Maybe you'll remember this. They're not trained to do statistics. They have to learn from you about methodology. And you have to learn from them things like what's the careful statement of the problem and the nature of the data. Okay, let me go faster now. This is just a bunch of thoughts that I've come over 20 odd years. Okay, one of the problems is that modern statistics is just too big. I think it's about the size of physics, and it's even bigger than astronomy. So it's very hard to find what you want, and they have terrible jargon. The Mantel-Haenszel test, the Anderson-Darling test. I always have 2 names, okay? Okay, so you can never figure out what it is. And there's usually half a dozen ways of proceeding. And a statistician you're consulted often is very vague. They won't even advise you. I once asked James Berger, one of the most distinguished statisticians in the world, who, by the way, is right here at Duke, a clear question, and he wouldn't give me advice. He just wouldn't do it. He doesn't want to tell me what to do. I found that really annoying. Just tell me, Jim, come on. I'm sure he knows. So it's very confusing once you get into statistics. It's just so big. Some statistics is based on mathematical proofs. There's a theorem. Jogesh Babu wrote a theorem in 1982 of great importance to something I forgot, bootstrap theory or something. And if there's a theorem, the astronomer cannot violate it. It's perilous to violate the theorem. Okay? But sometimes there is no theorem. Sometimes the issues are still being debated. Sometimes they've been settled. And sometimes, very rarely, this is wonderful, I love this. There's a theorem, there is no theorem. Huh. This is not trivial. Look up in Wikipedia, sometime when you're bored with me. Look up in Google, the no free lunch theorem, 1990s, by two statisticians, that you don't know what machine learning classification method to use for any given problem. Should I use support vector machine? Or should I use random forest decision trees? Nobody can tell you. There's a theorem, there's no way to know. Oh, that's bad news. Okay. I have to get up. Okay, that's bad news. So they can't even tell you definitely what's going on. That's why Jim probably doesn't answer my questions. Okay. And I'm very worried. I'm an editor of a journal, a statistical editor of a journal. And I'm very worried that the results being reported are not because it's a stupid method, but because they made arbitrary choices in methodology and arbitrary choices in variable scales. And so I actually worry that the results depend on using units like parsecs or kilometers per second. And some methods, like classification methods, most of them are scale dependent. So you generally want to use scale invariant methods so it doesn't depend on your choice of units. And by units, I'm talking about miles or kilometers. Imagine your science changed if you converted units from miles to kilometers. That's not reliable science. A whole lot of statistics is scale dependent. Okay? So it worries me. Okay. So I like non-parametrics or a few scale invariant methods just to you just sleep better. And basically my advice to astronomers is, look, if there's 5 ways of doing it, don't try to choose one, just do all 5. And think afterwards. Think. And it's hard to interpret the meaning of a result. You run a test, you get a probability, a p-value, you do something, you get a result. What does it mean for my goals? It's not obvious. Okay. So astronomers should become more knowledgeable in the use of statistics, and that's a big educational job, and more judicious in interpreting the results. It's not so clear or straightforward what the results are. Okay, let's do some history. For most of Western history, the astronomers were the statisticians and the statisticians were the astronomers. So let's go to ancient Greece. Astronomical problem. How long is a year? 365.25 days in a year. That 25 is important if you are an agricultural society, because if you don't get it right, then your calendar slips and you don't know when to plant your crops. And this is what happened. Julius Caesar had a calendar. 1400 years later, it was off by 2 weeks. And Pope Gregory had a new calendar. I think it was 1100 years. And you got to get it right. There's 2 ways of getting it right. One is you build a telescope called Stonehenge, and you measure the year every year with a very expensive instrument. You know what Stonehenge is? A ring of rocks in England, 5,000 years old. I don't know if there's any in the Far East. Does Korea and China have rings of stone for calendars? Oh, Americans have it. Europe has them. Europe has a lot. They do it for calendars. The other way of doing it was invented by Hipparchus, great philosopher of Greece. You look at a well in Greece, and the same day you look at a well in Egypt, and you look at the angles, and you calculate, and you can do it once. So he did it a few times, and he got 363 days, and 367 days, and 365 days. How do you average? How do you get one number when you have a discrepant measurements of the same quantity? So what Hipparchus said is take the smallest one and the biggest one, and just go in the middle, where there's no measurement. Do we do that today? No. It's too sensitive to one big mistake. Outliers. So in medieval times, theologians thought about this, and they were worried. The more measurements you make, the fatter the distribution gets. So they thought the most reliable thing is to measure it once and stop. Then you know the answer. How do you like that for statistics? Interesting. Tycho Brahe, the great astronomer of the 1500s, who observed without lenses, he actually understood a lot. He calibrated his observers. He did an amazing amount of statistics. He recommended the mean. Add them all up, divide by n. Galileo recommended the mean. Next generation. It wasn't solidified until the 18th century. All astronomers use the mean. So, what if I went to Duke and UNC and North Carolina State and interviewed all the statisticians and said, I'm measuring a physical quantity, I have multiple discrepant measurements, what should I do? I'll make a bet. More of them would say the median, not the mean, because it's more robust to non-Gaussianity and outliers. In other words, for 2,500 years, we still haven't agreed. How do you measure the central location of measurements of the same thing? Interesting. That was astronomy. Astronomers were the center of this debate for 2,000 years. Then we got Newton, and Newton gave all these ellipses and all these formulas of the masses and the angular momentums and all this. Now we can actually get real astrophysical quantities. We can determine the properties of the orbits perfectly. And we didn't have to guess our way along. So Legendre, Laplace, and Gauss were competing in around 1810. And in different ways, they basically developed the Gaussian normal distribution and least squares theory simultaneously, regression. And prominent astronomers contributed to least squares theory throughout the 19th century. This sentence is not well known. This is well known. So astronomers basically developed. Do you know what Gauss's job was? Gauss was a mathematician, a great mathematician. His job, director of an observatory. He was doing budgets and personnel for astronomers. Okay, that was his job. Gitten, I think. So, the astronomers and statisticians for 1,000 years are the same people. They're all talking to each other, all doing things together until 1900, roughly. What happened? The statistician discovered humanity, human affairs. R.A. Fisher worked for Her Majesty's Agricultural Service, manufacturing. Others worked for the military purposes, or for government, or for social sciences like sociology, demography, political science, economics. And the astronomer, who used to know all of statistics, yes, they used to be the statisticians, we discovered quantum mechanics, thermodynamics, the rest of physics. We already knew gravity. So we became astrophysicists throughout the 20th century, and you guys became social and biological scientists and manufacturing. And by the time I came around, I was educated in the 70s, basically, in 80s. 0 classes in statistics. How many classes in statistics? 0. 2. Okay, you're ahead. But you're self-selected to be here. Okay? So the average among your peer group is probably 0 to 1. And the 1 was lousy. It was all stupid. It was useless for astronomers. Okay, so as a result, astrostatistics was dead in the water, and astronomers started getting more and more data, more and more complicated modeling problems, and didn't know anything about, let's say, post-World War II statistics. We didn't know survival analysis existed for censored data. Is a good example. Okay, so as a result, today, 2010, things are not so great. Many astronomical studies are still very much confined to old-fashioned methods, from Fourier analysis, least squares regression, weighted least squares regression from Pearson. We call it chi-squared. Kolmogorov-Smirnov, goodness if it, we don't even realize that the Anderson-Darling test is better, is more sensitive. It does the same thing, it's just better. We use principal component analysis since the 1970s, but that's all we know about multivariate analysis as a community. This is the lower half of the community is stuck here. Okay, and we sometimes use it all wrong. It's really pathetic. Okay, that's about half or 2/3 of our community of astronomers are like me trying to fix my house with 2 screwdrivers and a wrench. In particular, we've lost most progress of the 1970s, 80s, 90s, and zeros. We don't know much about maximum likelihood estimation. We never learned the EM algorithm except that one of us reinvented it. We don't know about the Bayesian information criterion, and we used the bootstrap a little bit, but not enough. Most of us don't know about multivariate classification. If you don't know this, linear discriminant analysis from Fisher, support vector machines from Vapnik, classification of regression trees from Bryman. Random forest is an elaboration on that using the bootstrap. In time series, which is this semester, we never learned autoregressive models. 0 papers on ARMA. 0 in the major literature. We've never used state space model. 1 paper by one brilliant astrostatistician who's now working for industry. He left. Spatial point processes, we never learned Ripley's K. We invented our own, which is the differential of it. It's not as good. We're reinventing Kriging, which was already there for 40 years, but we didn't. I discovered survival analysis by multiplying by -1 and visiting an astronomer. I didn't do anything. Okay. We're not reading computer vision literature from the engineering schools where they spend billions of dollars to analyze images. And we're not learning R, which since 2000 has grown exponentially to encompass most of modern statistics. And the purpose of the textbook that Yogesh and I do and the tutorials and the summer schools that we run for astronomy grad students is basically catch up. Just catch up briefly to sort of last 50 years. That's useful. Using astronomy examples, astronomy language a little bit. It's just catch up. Most of this book, senior level undergraduate statistics class. It's not that difficult. Most of it is undergraduate statistics classes, but a lot of them, 6 or 7 different classes. But astronomers have a lot of problems. It's amazing. So here is a very important field of astronomy called cosmology. And here's about a dozen sort of details. Some of them have hundreds of papers and dozens of groups around the world working on them, of problems in cosmology. And this is my effort to try to translate it into statistics. And the amazing thing about it is the variety of red topics. A single topic in astronomy, let's say a single topic in, I don't know what to say, let's say demography. You'd have to learn a couple branches of statistics. A single topic in astronomy, you have to learn regression, spatial point processes, density estimation, shape statistics, which is really bizarre, false discovery rate, multiple hypothesis testing, multivariate classification, Markov fields, Bayesian inference, and this one, and actually it's called uncertainty quantification, and so, but it's very new. It's being talked about at SAMSI. You basically have to be an expert, brilliant PhD in astronomy to do cosmology. And you know what? It's actually true. Most modern young cosmologists have learned some specialized field of modern statistics very well. Particularly Bayesian inference is very common. So that's the bad news. The good news is that things are getting better. We've improved access to software. R is available, and some of us are learning it, but even Python is much better than the predecessor like IDL. The papers that in astronomy that have statistical methods as the keyword have doubled in the last decade. There's hundreds of papers that say, ooh, this paper includes statistical methods. Not all of them are new, but there's an interest in this. We run short training courses here, and I go around the world I'm like a roving professor. It's really strange. For 2 years, I didn't get off an airplane, it seems, just because we wrote this book. Okay, it's weird. We wrote the book, but the local professors of astronomy can't teach it. That's why I went there. The 50, 60-year-old astronomers don't know this. They don't know undergraduate level statistics. Whew. There's now research collaborations. Oh my God, I should put Samsi here. I guess Samsi's here. Okay. This is an obsolete slide. It should say 2016 there. Oh, I'm sorry. This slide is a year old. I got to improve this slide. So anyways, we're now having research collaborations at Harvard, at Carnegie Mellon, at Penn State, at Stanford, at Cornell, at Imperial College London, and many of those collaborations in America are represented here in SAMC. You're like a collaboration of collaborations here. And there's conferences and meetings that are happening more and more. And all the scientific societies sort of woke up in the last 5 years. So in statistics, you have the ISI. They do the World Statistics Congresses. So they formed a whole association called the International Astrostatistical Association. You have the ASA, American Statistical Association. They have an interest group in astrostatistics. We have the IAU, and we have a commission on astrostatistics and astroinformatics. I happen to be the first president of it. The American Astronomical Society has a working group as well. And the LSST has a collaboration. And several people associated with this are here at SAMC this year. And the IEEE just opened up a task force for astronomy. So it's like, whoa, it's like rapidly growing interest. There are meetings and workshops and hack days and all sorts of things popping up all over the world, sort of spontaneously, because of the last slides. We have a growing sophisticated need for sophisticated methods. We are not trained, so we're quickly trying to catch up. So the mood today is much better than when Jogesh and I started 30 years ago. Much better, a lot better. We're happy, okay? Jogesh Babu created this SAMC program, okay? One of the main things is just big data. So big data is when I say there's going to be 40 billion light curves, or I'm dealing with 200,000 light curves, or finish the sentence. There's petabytes of data out there. So this is fairly recent. It's been more or less the last 10 years. It started with something called the Sloan Digital Sky Survey. And a small telescope, only $100 million, produced a gorgeous, gigantic, uniform data set from which 5,000 science papers have been written. Really brilliant papers. Sloan, SDSS, Sloan Digital Sky Survey. That was the critical one. And since then, this is a telescope that makes surveys. This is a telescope. Oh, the head of this is Ashish Mahabal. He'll be here. I don't think Pan-STARRS has people here, but I'm not sure. This one, and then LSST is the big one coming up. And all of us are involved in LSST, or will be, because it's the national project of America. We have another field, I won't go into it. Some of them create data cubes, three-dimensional images, and we have a whole field called radiointerferometry that makes data streams that require the fastest computers in the world just to process the data. And then we have a virtual observatory to try to bring together the databases, although it's not working very well. But basically, we need a lot of powerful tools to derive data insights from terabyte, petabyte, and the whole community is moving into exabyte. Big data. Astronomy is one of the scientific fields where big data is here today. It's not hypothetical. It's here today. We're not as big as Google and Amazon, okay? But we're big for science. So this means that we now have informatics. And informatics and statistics are not the same, but they're closely related. How many of you are interested in big data and informatics and data analytics, things that are sort of on the boundary between computer science and statistics? Okay, well, I just want you to know this is big. This is where the employment is going up exponentially, okay? Data analytics. By the way, when they do an interview of the data scientists in the country, say what languages you use, it's equally divided, Python and R. And most of them say both. So you should know Python and R if you want to go into business and do marketing for retail companies, whatever. Anyways, there's a whole lot of informatics going on. We just had our first IAU informatics meeting just a few weeks ago. The good news, again, there's now 4 textbooks, modern textbooks of statistical methods for astronomers. Phil Gregory on Bayesian. Wall and Jenkins is a thin paperback that you can learn in a semester, and beautifully written, but no software. This one has Mathematica that nobody uses. We are using R, and this one has almost the same titles, but emphasizes more big data. It uses Python. This gentleman here, these 2 gentlemen, are leaders of LSST. This gentleman, professor of computer science, gone into startup industry. And these societies. You can join the societies. Particularly this one here. The IAA, the International Astrostatistics Association, it accepts everyone. I mean, you can't be a plumber. But I mean, grad students in stat, grad students in astronomy, you can join the IAA, no trouble. You could join the AAS working group if you're a member of the American. You could join the ASA one if you're a member of ASA. Okay, so join them. They're cool. And a couple of us run a website called AS, Astrostatistics, AI, Astroinformatics, P, ASAIP, portal. And here, this is what it looks like. There's 2,000 recent papers, and you can search the recent papers. You can put in Bayesian image processing. Don't put in something about astronomy. Put in something about methodology. And it will give you all the recent papers in using those keywords. Go to meetings. 40 a year. Workshops in Korea and Africa and many in America and Europe. Some are big official international conferences and some are little tiny hack days. Listed here. Resources. Includes job listings. September through December every year, we put job listings on. It's tripled since we started in 2012. The number of jobs in astronomy that say we want people skilled in statistics and informatics has tripled in 3 years. This is a growing field. LSST hasn't even been finished yet. It's going to grow even more when LSST comes along. So the purpose of this is to serve the community, so to be a place to talk. Oh, even better, I should put it on the same slide. There's a Facebook group. So since you're of the generation, well, Facebook, I want you to know my generation doesn't use Facebook except to speak to kids and grandkids, but you do. Go look for a group called, not a page, a Facebook group called Astrostatistics. 2,000 members. You just join. It's really cool. I'm jealous because we tried to do that on ASAIP with a clunky old clone site and nobody would talk. And this kid from Australian radio astronomer named Aaron Robotham starts this Facebook group and it grows like wildfire. Okay? So of course I'm wrong and he's right. Facebook is the way people communicate today. And okay, so this is my last slide. What do I imagine? Well, I imagine that we actually have courses in astrostatistics and in astroinformatics in every university like UNC and Penn State. Penn State, we're advanced. We're actually getting those classes today. You guys are behind. You've got to work on it. Okay? You're faculty. Pressured by the students. I'd like to see some astronomers get a master's in statistics so they actually learn something from the real people who teach it. Okay? Why not? We're perfectly capable of learning the stuff. We just haven't bothered to learn it. Okay, you want to hear my joke? I go to astronomers. I was at NASA and ESA, European Space Agency. So I go to ESA, and there's a room full of engineers and students and postdocs. And I say, this is not going to be very difficult. I said, it's not rocket science. They teach it to sociologists. Okay, it's not rocket science, and you are rocket scientists. So astronomers are as smart as rocket scientists because we are rocket scientists. Okay, so it's not that hard for us. So let's do it. Let some of us learn, become professional at this. Okay, let's fund it. It's very hard to get money for astrostatistics. Okay, a couple of the people in the SAMC are funded, but not enough. And let's use more things in R more wisely and more flexibly. And let's have our meetings, our research meetings are once every 5 years with 120 people. Come on, guys. Why aren't our meetings every 2 years with 500 people? Because astronomers don't view themselves as astrostatisticians, as methodologists. So they don't go to the meetings. So they don't talk enough. They don't learn enough. The field is beginning to grow, but really has not fully grown. So by coming to SAMC in 2017, you're coming at a time where it's no longer pathetic and bad, but it's not finished at all. It's not just not finished at all. It's going up somewhere. It's an interesting time to learn on the interface of statistics and astronomy. Okay, let's take a break. What time? Okay, we're now back, and let's talk about time series analysis from an astronomical point of view, not from a statistical point of view. So, time series in astronomy, what are we talking about? Well, it ends up that just like cosmology understanding cosmological data involves many fields of statistics. We actually have many types of time series or variable phenomena which we record with time series. In particular, we have periodic phenomena. That means the same thing happens repeatedly with a well-established, fixed period. We have stochastic phenomena. Things sort of wander around and change in some sort of, not just Gaussian white noise, but some sort of correlated stochastic phenomena. And we have explosive phenomena, things that happen once and don't happen again. Things that go bump in the night. Okay, so let's talk a little bit about this. So the obvious one, the one that dates back to celestial mechanics of the 17th and 18th centuries, is two objects are orbiting each other. And they orbit the center of mass. So you have a star and you have a planet. You have two stars that go around each other. And if you had enough time, you could see stars going around in a galaxy. But that takes except for the very center of our galaxy, where it takes only tens of years. It's mostly millions of years to go around. We don't see those. So most of this is binary stars and exostellar planets. But we also have things that are more or less fixed in shape that spin, and there's something going on at one spot. Maybe a beacon of light comes out, or it's darker there than it is elsewhere. Sometimes these are not really solid bodies, they're really gaseous bodies like Jupiter or like the Sun, stars, stellar rotation. But sometimes they're solid like neutron stars, and that's what radio pulsars are, and X-ray pulsars. We also have these stars that sort of are like jellyfish. They go bloop, bloop, bloop. They're not exactly stable, but they're not really exploding. They're sort of partially, they're stable, but they're pulsing. So we have pulsation stars. The sun actually has a very, very complicated pulsational spectrum with millions of frequencies known. The famous one that does big pulsations are called Cepheid variables and our Lyra variables. They were discovered early in the 20th century in our galaxy and soon in other galaxies. So we have the effort of finding periodicities and finding what the period is and otherwise characterizing the periodic phenomena. So in that sense, it sounds awfully like we should use Fourier analysis, which collects the information as a function of frequency instead of as a function of time. So it may be hard to see it in time, but in frequency domain, it may make a very strong signal. So Fourier analysis is often used in astronomy. In fact, that's the single most common traditional time series method is Fourier analysis. We have stochastic phenomena, where it's not just Gaussian white noise. We always have that in our detectors and sometimes in the sky as well. But now we're talking about things where something is falling onto a star or onto a black hole. A star, a white dwarf, a neutron star, or a black hole. And it's called accretion. When gas falls onto an object, it's called accretion. So if they fall onto a white dwarf, they're called cataclysmic variables. They fall, and several other names. They fall onto a neutron star, they're called X-ray binaries. They fall onto massive black holes, they're called Seyfert galaxies and quasars and several other names. So there's classes and classes of these within the category of just accretional systems. There's lots of subcategories of them. So the typical way, if I would just make it sound, it's in light, not in sound, would be like that. Okay? In fact, I was looking this afternoon, I couldn't find it. Let me try to dig up for you the most astonishing, I'll do it at the beginning on next Wednesday. The most astonishing accretional system in the world. It's just phenomenal. It's a gamma ray source in the Milky Way galaxy that's accretion onto a black hole. It has something like 20 totally different variability states. It literally is like a dissertation in time series analysis in just one spot in the sky. Nobody understands it, either astrophysically or statistically. So that can be very complicated or relatively simple. There's scintillations, which I won't go into, and then there's jets, I won't go into them. There are other sort of things which go like that. Okay. Then we have explosions. The most famous one of them is, remember I said the center of the sun is like billions of hydrogen bombs exploding all the time? But it's in the middle, we don't see it. We only see the nice yellow light on the outside of the sun. But on occasion, there's a thermonuclear explosion, hydrogen bomb, on the surface, particularly on the surface of a white dwarf, when it's called a recurrent nova, or on the surface of a neutron star, when it's called an X-ray burst. And those will go boom. The thing goes brightening up factor of a billion for a few hours or days or weeks, or X-ray burst could be for minutes and then dies away. Sometimes that happens over and over again in the same object. Another kind of explosion is sort of different. It's called magnetic reconnection events. This doesn't happen anymore, but when I was a kid, there were things you would have in your home, like, I don't know, a record player or some device, and a kid would touch it and get an electric shock. If you put your finger inside there, you go, ouch! Okay. Now, that's completing an electric circuit explosively. Now, but these are completing magnetic circuits. So you have a magnetic loops coming out of a magnet, North Pole, South Pole, and you have another magnet, and you sort of intertwine them, and they get tangled, and then all of a sudden, they reconnect. And that immediately releases explosively energy, magnetic energy, and can accelerate particles up to enormous energies and can heat up plasma to millions of degrees and things like this. The sun does this. It's called solar flares. I'll show you something in just a few minutes. If you have lots and lots of solar flares superposed, it tends to look stochastic. But if you see only one of them, it looks like just boom. Okay. And then the famous one is an entire star explodes in an instant. So this only happens very rarely. Only certain very massive stars go supernova once. Then they're gone. They leave behind a neutron star or a black hole. The rest of it is this expanding shell that goes out. So that's called a supernova explosion. Then they discovered these strange gamma ray bursts in the sky, these pew, pew, pew. I'll show you some of that time series in a few minutes. And we now see about one a day. And it's something to do with supernovae, but not all supernovae make gamma ray bursts, but some do, and it's being investigated. It's a relativistic fireball jet coming out of a supernova explosion. It's amazingly bizarre and exotic and energetic and deadly. You don't want to be near a gamma ray burst. You don't want to be near a supernova. Okay, it's not safe. Okay, so as a result, we look up at the sky. If you look sufficiently carefully at different wave bands, the radio sky is extremely variable. The X-ray and gamma ray sky is very variable. The visible light sky is actually constant. Every night you go out, you'll see the same stars, the same brightness for this lousy telescope. But if you take a big and better telescope with more sensitivity and more precision, you look at 0.1%, not just approximately how bright is it. Many, many things in the sky are variable, even in the visible band, but particularly in X-ray and radio. Okay, so we have lots of variable things out there to study that will tell us something about what the accretion process is, or the explosive magnetic processes are, or just sort of saying, hey, what's that class of objects? I wonder what's going on. I mean, some of them are like blazars. I mean, they were puzzles for years. No one knew what a blazar was. Okay, now we know it's a massive black hole, accreting gas, shooting out a relativistic jet that's pointed right at you within 1 degree, and you're seeing special relativistic effects. It's totally bizarre. Totally amazing. All that came from time series analysis of some gigahertz radio source or something. Okay? But unlike reasonable time series that come out of human affairs, where people can control the nature of the data, we have really crappy control over our data acquisition. A typical thing is, you want to study a variable star. The sun goes down, you open the dome, you turn the telescope, 8 o'clock at night, you look at it 8 o'clock to midnight to 4 a.m., and then dawn comes. And you can't look at it till 8 o'clock tomorrow night. So you have this daily gap in your time series. And then sometimes the moon comes up for a month, and it depends on the field, but some things you can't look at when the moon's up, it's too bright. So you say, okay, look, I'm just going to go into outer space. I'm going to go into a satellite. Well, the old satellites, 70s, 80s, 90s, and zeros, all went around in low Earth orbit, because that's the only rockets we had. And every 90 minutes, the Earth would eclipse what you're looking at. And nowadays, we take our satellites and put them far away. And they're really good. We get almost continuous data sets. Yay, finally. Okay? The 2010 era satellites are almost all far away from the Earth. And the worst one is the dreaded TAC, Telescope Allocation Committee. You write a proposal. You're a graduate student, you're a faculty member, you're an astronomer somewhere. I want to use this telescope, which I have access to, and I want to use it to study a variable star. And I need an observation once an hour for 5 nights in a row. And I give you 2 nights of data separated by a week. Because everyone else is competing for the telescope, and you just can't get what you want. And the telescope allocation committees more or less prevent reasonable time series acquisition from shared telescopes. The only way to do it is to have your own dedicated telescope. And people started doing that in the last 10, 15 years. They'd build their own telescopes just to get away from the darn committee, so they can get their time series reasonably. And also, here's another strategy. Only a couple of groups are doing this. They put a telescope in Chile, which is the best place in the world for a telescope. And they put another one in South Africa and another one in Australia. So when dawn comes in Chile, they look at the same star quickly that night. In South Africa, when dawn comes, they look in Australia and they get 24-hour coverage, and they get rid of this one, the daily cycle. Yay! I mean, that costs tens of millions of dollars to arrange that. It's enormous hassle. Almost nobody does this. But you can see why people are trying to get away from gapped data streams. Big gaps. Some of the gaps are awful. Oh, I guess I should say Telescope Allocation Committee and also human psychology. I don't mean to say it. These guys are going to get Nobel Prizes probably. But do you know how the old timers still go out and look for exoplanets? They go to a telescope and they have a list of a few hundred stars and they say, which one should I look at tonight? I sort of like that one. I'm going to look at that one tonight. And they get some data that night. Excuse me? How are you going to analyze your data afterwards? How are you going to take your Fourier transform that assumes evenly spaced data? How are you going to calculate an autocorrelation function that assumes evenly spaced data? How are you going to do anything in any textbook of time series analysis when you just sit there and you just make up your observation time just by whim? It's really bad. It's really a problem. Sometimes unavoidable. Sometimes we could do better if we only thought about it. Here's another one. Heteroscedastic measurement errors. Heteroscedastic means different for every data point. That's for you, okay? But it's just jargon, okay? You and I are familiar with this, Charlie. We see it all the time. You look at something faint, you get a much bigger uncertainty. You look at something bright. Maybe you're only allocated 15 minutes, and to get the high precision, you really need 2 hours, but you don't have the time. So you get low precision, low accuracy, big measurement errors. Sometimes there's a cloud in the way and the data's lousy or the electronics aren't working that night. You get low quality data. Or the point spread function is variable. The telescope gets fuzzy because the atmosphere changes a little bit. Okay? So we have these all the time. Amazingly, astronomers actually measure their measurement errors. Now, if you happen to have been consulting with social scientists, you don't have that. Social scientists can't measure the variances of their measurement errors. We can. Not only that, but we are taught, we're not taught statistical methods, but we're taught to measure our measurement errors by our professors. What we do, for instance, is we look at an image in the sky, we measure the brightness of the star or the quasar or the galaxy, and we go right next to it where there's black sky, we measure the noise. That's the measurement error on that one. The noise is high, then it's low precision, low signal to noise ratio. Okay? Or we do it in time. We look something on and off, something like that. So the signal to noise ratio differs from point to point. Sometimes this is not really a problem, but you just got to be aware. Sometimes the data come in individual photons, ping, 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 instead of real valued measurements of sort of large numbers of photons. That's not really a problem, but you got to be aware of it. And then the other problem is just the previous slide. There's just too much going on. You don't know what you're looking at unless you know your target ahead of time. So you don't know, am I supposed to look at Fourier analysis? Am I supposed to do autocorrelated analysis? Am I supposed to look for change points? That's the jargon in time series analysis. Completely different mathematical statistical approaches for these classes of phenomena. So the answer is, if you don't know what you're doing, you got to look for all of it. And we do. We actually look for all of it. Okay. So let's now show, this is the next, no lecture anymore. It's just, I think I'll use the word a gallery of time series. The first one is my project with my colleague Costa Getman. So we got 3 weeks of time on the Chandra X-ray Observatory, $4 billion observatory, okay, and to make the world's best movie ever made in X-ray astronomy. So think of this costing, I don't know, $10 million. No, it didn't actually cost me. It's just I used a month of time of a $4 billion telescope. Telescope's still running, 18 years. So it's a picture of the sky. It's about the size of the full moon, this picture. This is several thousand stars. It's in the Orion Nebula. It's the Orion Nebula cluster. And this is in X-rays. The colors are fake colors representing the energy of the X-rays. Actually, these are Poisson processes. They're not actually grayscale. So now we're going to zoom in. Now we're going to see 13 days of data. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, I got it wrong. Everything you saw there was statistically significant. Every single X-ray source in this picture is variable. So, Costa and I spent years making that movie. It was hard. I'm sorry. I want to get to something that says full page. How do I do that?
Were we down where it says full screen mode?
Oh, there it is. Thank you. I just didn't see it. Thank you. Okay. So now, I've taken 2 of those sources on that movie and showed you the 13-day time series. So the first one's a typical one. It's rather weak. And that shows the Poisson noise. Ping, 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 and then there's a gap. This gap is every 2.5 days because the satellite has a weird orbit around. So there's a gap when it comes near the Earth, and then it goes out in outer space again and goes ping, 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 and then all of a sudden, ping, 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 ping. For a few hours, the brightness went up, I don't know, factor 10, and then it went back down again. It ends up, this is related to solar flares. This is a star, it has flares and X-rays, and this, except they're 1,000 times stronger than on our sun, because our sun is quiet and these are very loud. Here's another one, but this one's much stronger. Okay? And there's another, the little dots is every single photon, and the height of it is actually, this axis here shows that every photon is tagged by something called a Mark variable, or an ancillary variable, which is the energy of the photon. So this is not actually a univariate time series, it's actually a bivariate time series. And in principle, it's actually 4 variables. But Aryan right ascension declination don't apply in this case. So we actually have not just the number of photons, but also the behavior in the energy dimension to think about. And that's one reason why there's 2 colors up here, is again, a split in energy. So we wrote papers and papers about this. Okay, here's the famous gamma ray bursts, which are some sort of explosions that are happening associated with supernova. And this is a satellite that's still up, NASA's Fermi Gamma Ray Space Telescope. And 1, 2, 3, 4, 5, 6, 7. This is 14 gamma ray bursts. So you can't read it, but the time scales are in seconds or tens of seconds. So this one's about 10 seconds long. So this is real time in the sky. 10 seconds. I can't quite read that. Some of them are a fraction of 1 second. Here's one. That's about 60 seconds. This one's about 5 seconds. This one. This one. This one. Nobody understands those variations astrophysically. We really don't understand it. These were discovered, when they were first discovered, they were total mysteries. It was one of the greatest mysteries of the late 20th century. And then we figured out it has to do with relativistic fireballs coming out of newly formed, the birth of black holes. So that's called the gamma ray burst prompt emission. It's followed by afterglows that can last much longer and are much smoother. So here it is. This is log of time. And so this is another satellite called NASA Swift satellite, which is also still working. This is hundreds of seconds, thousands, tens of thousands of seconds. So this would be minutes, hours, days, maybe the last point is weeks. So it ends up the brightness is simply just going down. It's very bright, and then it gets fainter and fainter and fainter. And it seems to follow more or less a straight line. Actually, it's two broken lines, segmented lines, in a log plot. So this is a power law distribution of X-ray flux as a function of time. But when you make a power law model, there's some deviations, which are these X-ray flares. This power law is in the astrophysical theory. They understand that. But these flares that deviate, they don't understand that. Something is falling onto the black hole or falling off of it or exploding from it. Nobody seems to know. Okay, I mentioned solar flares and magnetic reconnections. Here, you probably haven't done this since you were a child. But do you remember they would give you in school a magnet and little pieces of iron filings, and you would see these like patterns on the magnet? That's what this is. It's like North Pole and South Pole, and these are the magnetic lines connecting them. This is on the sun. This is happening today. The sun looks like today. You don't see it in our eyes. First of all, the sun's too bright. But all you have to do is go in the ultraviolet, which is what this satellite does. And it sees these things. And this one is a European X-ray satellite. For this event, this one exploded like that. So this is, again, kiloseconds. So 3.5 of this is about an hour. So this is a few hours long. So it's going, oh, sorry, here's the actual data. And they decomposed it into something that's smooth, that lasts about an hour, and a periodic, and they can actually see them flopping back and forth, oscillations in the magnetic loops, and that tells them all sorts of wonderful things about the magnetic fields of that part of the sun. So this is solar physics. There's a lot of time series in solar physics. I thought this would be after the other slide. Oh, well, I'll do it now. So the first thing they did when they discovered, I'll do that in a minute. In 1995, they discovered the first exoplanet in a way I'll show you in a minute. And then it was found again and confirmed by a very young astronomer named David Charbonneau using a very simple telescope, almost like you could buy for your backyard for a few $1,000. He discovered that here's the time series. So this is in days, 0.2 of a day. So this is a few hours. It's 100% of the brightness, and then it went down to about 99% and went back up on September 9th. And a few days later, he found it again. And the times that he saw this were agreed with the times that the planet was going in front of the star. And it was eclipsing like 1% of the light of the star. So this is a occultation by a planet orbiting another star. And this was discovered by David Charbonneau. David Charbonneau, for this paper, won the highest prize for a young scientist and is now a distinguished assistant professor at Harvard. By the way, he deserves it. He's a brilliant man. He's a brilliant young man. Okay. So this was one of the most famous papers in modern astronomy. By the way, by knowing this 1%, you can get the radius of the star. If you know the radius of the star, you can get the radius of the planet. So the radius of the planet was 1.25 times the radius of Jupiter. And you also get some knowledge about the orbit. It has to be very close to right in front of you, because if it orbits this way, it wouldn't go in front of the star. So the inclination is always very close to 90 degrees for this to see. So we only see a small fraction of these eclipses where the orientation of that orbit happens to be very, very close to our line of sight, just by chance. Here's another one which I decided to show. It looks almost the same thing. 100% goes down to 98%, goes up to 100%. Here's an average of the data. This is just average, and it makes a nice eclipse. But this one actually, it's 6 years later, is actually much more difficult. This one could not be done in your backyard. This is the secondary eclipse. The first one is invisible light. The planet goes in front of the star and blocks out a little bit. The other one is in infrared, where it's bright and it goes behind the star and gets a little fainter. So this is actually at 24 microns, which is in the mid-infrared. It's very difficult to observe at 24 microns. This one's done in outer space using the Spitzer Space Telescope. So there's another, you learn different things from the two measurements. This one you learn something about the temperature. What do you learn? The temperature of the surface temperature of the planet, I think, is what you mostly learn here. Maybe something about the reflectivity of it. I'm not sure. Okay, this is how they were first found, by not actually looking at the brightness as a function of time, but by looking at its radial velocity. Radial means towards you or away from you, along the radius. Okay? So there you are, you're an astronomer, you're sitting on Earth, you take a telescope and you're looking at the star, and sometimes you find it actually is moving away from you, which is positive velocity, and sometimes it's moving towards you, negative velocity. And if it goes around periodically, it's in orbit around something. Okay, that's cool. So, what's the amplitude of this? This one's a very, very big example. A very, very big planet is pulling that star back and forth. A very big example is 100 meters per second. Ladies and gentlemen, the speed of light is 300 million meters per second. So this can only be seen, this is 1 part in a million, less than a part in a million. So you can't even get these measurements to figure out how to measure the velocity to, just outrageously precise measurements. So the reason we didn't find these planets in 1930 or 1960, we had to wait till 1995, is simply the precision of the measurement. Very boring work to just improve the calibration and get the temperature stability down and to put scramblers in the fibers, all sorts of technical engineering. It was very boring. Nobody thought we'd ever find planets in my lifetime, because if it was like our solar system, we would never have found it. You know what these are? They have a Jupiter size or Jupiter mass planet inside the orbit of Mercury. So it really pulls the star back and forth and makes takes out 1% of the light. And if it was our solar system, Jupiter's way out there. We would never see it at all with our technology. We need another factor of 100 sensitivity. We don't have it. So we discovered the planets because there were these hot Jupiters. Nobody expected them. It was flabbergasting 1995 when Michel Mayor and Didier Queloz, with a very ordinary telescope but an extremely precise spectrograph, discovered the first radial velocity inside of a planet. And their rivals were at the Keck telescope in Hawaii, a bigger telescope with similarly specialized, stable spectrograph. They confirmed it. All this was published in Nature magazine in 1995. So, report, 2 weeks later, confirmation, much smaller error bars because it was a bigger telescope. This is another one of the early ones. This one's called HD 73526. You don't have to know the names of these stars and galaxies and planets. It's almost as bad as statistics, the way we name things in astronomy. This happens to be a catalog of bright stars that was done in 1905 or something. So there's about 500,000 of them, I think. So look at the data. This is days. 360, that's 1 year, 2 years, 3, it's about 4 years of data. How many times did they measure it in 4 years? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 measurements in 4 years. Well, they certainly know it has variable. It's variable. It's not, none of them are consistent with each other. But it looks like garbage. Okay? Look at this. Phil Gregory. Here is the Fourier transform. This we don't call it a Fourier transform. We call it a Lohm-Scargill periodogram. You'll learn this from me or from someone soon. So, but it's basically a Fourier transform. And there seems to be a noisy peak here, but when you do a better job, as these people do, a Bayesian Lohm-Scargill, it's a stronger signal. And now that's 128 days. That's the best fit period. And now if you take those 17 points and plot them sort of modulo the 128-day period, all of a sudden they line up. And this is just a repeat of the 17 points. The star is going. That happens if the planet has an elliptical orbit. So they get the ellipticity of the orbit, the inclination of the orbit, the size of the orbit, the radius of the... No, they don't get the radius. The mass ratio of the star and the planet. They get a whole lot of astrophysics from this model. The curve is the model. You know who would recognize that curve? Laplace, 1700s. I bet Isaac Newton would understand it in the 1600s. Even Kepler in the 1500s was doing similar things. He was using Mars. But if you sat him down and told him the stars were suns and there were other planets, and some of these formulas are called Kepler's. Their formulas are named after Kepler. Kepler's equation, I think it's called. Okay, so here it is again in real time. So here it is with just time, 1,200 days. Here it is again, 1,200 days, 17 data points. Now that's the model. Now the model goes through the data perfectly. And here are the residuals. It's perfect. The scatter of the residuals is exactly that expected from the measurement errors, which are the error bars. So ladies and gentlemen, you're going to hear a lot about this problem because we have some of the world's experts here this semester at SAMSI. Astrophysical modeling of exoplanetary time series 1 and 2, and there might even be a third one. I wouldn't be surprised if some of the Gaussian processes involves the same sort of data. And I wouldn't be surprised if some of the autoregressive parametric modeling is similar data. This is very hot science, ladies and gentlemen. The discovery of planets is the most exciting thing that's happened. That and cosmology, precision cosmology, in the last 50 years. Basically, anyone who studied stars had to study planets because the prestige of writing and the funds for studying stars has plummeted, and all the money and all the interest and all the activity has gone to exoplanets. At a recent astronomy WAS meeting, it's like a JSM meeting, right, where there are lots and lots and lots of simultaneous sessions. I couldn't believe it. You'd go to a simultaneous session on quasars. And there'd be a room, mostly empty seats, 30 people in a room with 100 seats. You'd go to one on galaxies, 30 people, empty seats. Then you go to a session on exoplanets, completely full and pouring out of the hallway. So I went to one of the leaders of the society. I said, David, I said, what's going on? He says, 1/3 of the contributed talks this year are exoplanets. The field didn't even exist 20 years ago. It's extremely exciting. And to discover them, time series analysis. A very, very, very badly gapped data set sometimes, and not so badly gapped data sets other times. Oh, just to show you, these people are not fools. This is all a complicated Bayesian hierarchical model, and here are the one-dimensional marginal posterior distributions for the period, 128, with a range of around half a day, of a velocity, minus 30, of an eccentricity, which is 55%, of, I don't even know what S is, I forgot what omega is, and I don't know what chi is, and k is the amplitude. See, I don't really remember all these parameters. It's about a 7-parameter fit, 7-dimensional parameter space. So you need MC to jump around in 7 dimensions. But what if you have 2 planets? Oh, then there's 14 dimensions. What if you have 5 planets? Oh, this is so painful. Welcome, Professor Eric B. Ford. That's his specialty. High-dimensional Bayesian modeling. He's the only person I know in the world who needs GPU supercomputers devoted to his calculation with kilobytes of data. It's not big data. It's teeny data with huge computation. It's very odd. It doesn't make any sense. Usually huge computation is for huge data, but not Dr. Ford and other people like him. So it's really fun. It's a lot of fun. This shows 2-dimensional dependencies. Here's eccentricity as a function of E. It means that these are not simple, what do you call it, multivariate normal posterior likelihood, posterior distributions. They're very weird looking. They're strange bent bananas. And by the way, no one else, I asked Jogesh, I said, why don't you show all these marginals and all these dependencies? And he says, well, why bother? No other group is interested in the details. All they want to do is just find the maximum, most probable solution. They're not interested in the relationships of all these parameters. The astrophysicist is. The discussion by Rebecca Dawson and others will all involve studying these things. Oh my goodness, that's really interesting to them. See what I mean? They really care. So some of the most sophisticated Bayesian modeling, I think, anywhere is being done by astronomers. Some of them are visiting SAMSI this semester. So you're going to hear a fair amount of Bayesian modeling. If you don't like Bayesian modeling, you can go stay home, okay? Skip it. But it's very brilliant. It's brilliant, in my opinion. Well, that's it. I was reluctant to do this. The gallery I just showed you is totally inadequate. I have not showed you eclipsing binaries. I've not shown you Cepheid variables. I've not shown you my favorite weird black hole. I've not shown you the supermassive black hole called Sagittarius A star in the center of our Milky Way galaxy. You've heard of it, okay? But it has very weird flares in X-rays and infrared, I think. I forgot. There's a lot I haven't shown you. I haven't shown you most of it. I haven't shown you anything in the radio band. I really should. I feel guilty for making an inadequate gallery of astronomical time series for you. So, all I could say is, I didn't show you all of it. I showed you little bits of it. It is vast. It is varied. And we need, that means Charlie and my community, need time series analysis. But because of the problems I mentioned at the beginning, we can't use most of the standard stuff. We need specialized tools. Although I think some of the standard stuff can still work. So we need both standard time series analysis and special tools, research level tools. So you will learn from me after we learn R next week. You will learn from me 2 or 3 sessions in this class, classical textbook time series analysis for the astronomer. And you will learn from the visitors, and I will be giving one of the visitors' lectures, research level tools. Okay? So if you don't like the class, drop it. No one's forcing you to be here. If you think there's a friend of yours who wants the class, tell them to join in. I think there are people doing their dissertations who really need this class, who don't know this stuff. I'm talking about in astronomy departments. Okay, it's amazing. The needs are there. For the statistician, you're looking at, I don't know what to say. There's very few statisticians who know even as much as you just heard in 2 hours. Okay, this is not a popular area for statisticians. But Michel Mayor, he's going to get the Nobel for discovering the planets. The planets are really important. We now know that every star you look, most stars you look at night have planetary systems. That requires A, time series analysis to find a few thousand of them, and B, extrapolative techniques to establish the total populations. That's working group number 4. So we have 2 working groups at SAMC this semester on time series, and a third one on exoplanetary populations, the extrapolation, correction of what we, going from sample to population, D.R. Cox. This is just about as important basic science as I've ever seen. I've never seen a transformation of a field so rapid as astronomers and exoplanets. Entire departments have changed. My department has changed. The last 4 professors we've hired, all on exoplanets. We're not alone. It's really exciting and very, very statistical. You can't do any of it without brilliant, high-level statistics. So we need you, and the community of statisticians. We need us. We need our instrumentalists to do these, make these amazing spectrographs that are very stable and things like that. And we need people to live in the middle. I personally live in the middle. I'm not a brilliant mathematician, and I don't know how to build a spectrograph, and I live in the middle. I'm an astrostatistician. We need a few of me in the middle with both training, astro training and stat training. So this is great science in my opinion. So I am not embarrassed to say that the SAMC semester will do a lot of exoplanetary work. It is the most vibrant, booming field in astronomy today, for good reason. Well, ladies and gentlemen, do you know the time? It is 30 seconds before 7 o'clock. So I didn't leave much time. Why don't we say this? I think I'm going to start off on Wednesday, next Wednesday, asking you, what did you think about today? All of this is online. Okay. What did you think about the first lecture? What did you think about the gallery? What do you think about my ideas? And then I'm going to show you this one black hole that I just love, this time series thing. It's just, I got to find it. It's just so cool. And then we'll go do R. So bring your laptop and please try to load R before you start.